Section 1. The Edge of Possibility. In the quiet of a starlit sky, a question echoes through the cosmos. Are we alone? For centuries, humanity has gazed upward, searching for answers in the infinite expanse of the universe. The night sky has been our shared canvas of wonder, a tapestry of constellations that inspired ancient civilizations to dream and modern scientists to calculate. Today, armed with the power of modern science, we stand at the precipice of discovery. Our tools are no longer limited to the naked eye or simple telescopes. We have sent probes to the edge of our solar system, like Voyager 1 and 2, which continue to transmit data from over 14 billion miles away, extending our reach into the unknown. The distant world, Proxima Centauri b, orbits its star just 4 light-years away, a tantalizing neighbor within reach yet shrouded in mystery. Discovered in 2016, this exoplanet is a mere stone's throw away in cosmic terms, circling the closest star to our own, Proxima Centauri. Its proximity has sparked a flurry of scientific inquiry and public fascination. Is it habitable? Could it harbor life? These questions drive teams of researchers to push the boundaries of technology and imagination. The European Southern Observatory's telescopes in Chile, which first detected the planet, represent just one of the many global efforts to unravel its secrets. This is not just a story of distant planets and theoretical propulsion systems. It is a testament to human ingenuity, our relentless quest to bridge the vast emptiness of space and find our place among the stars. The journey to Proxima Centauri b, if ever achieved, would dwarf the achievements of the Apollo missions, which sent humans 238 hours, 855 miles to the moon. To reach our stellar neighbor, we would need to travel approximately 24 trillion miles, a journey that, with current technology, would take tens of thousands of years. Yet, the dream persists. Programs like Breakthrough Starshot, funded by billionaires and backed by renowned physicists, are exploring radical ideas such as laser-propelled nanocraft that could theoretically reach speeds of up to 20% the speed of light. Join us as we embark on a journey to explore the cosmic frontier, where science meets imagination, and where the future of human exploration hangs in the balance. The stakes are high, the challenge is immense, but the potential payoff unfathomable. What if, among the countless stars and planets scattered across the Milky Way, we found evidence of life? Or, perhaps more profoundly, what if we discovered that we are alone, the sole custodians of consciousness in the universe? These questions fuel our curiosity and drive us to innovate, to push beyond the limits of what seems possible. The cosmos is vast, almost incomprehensibly so. Our Milky Way galaxy alone contains an estimated 100 billion stars, and there are roughly 2 trillion galaxies in the observable universe. Every advancement in astrophysics and space exploration brings us closer to understanding our place in this grand tapestry. The James Webb Space Telescope, launched in 2021, is already revolutionizing our view of distant worlds, peering into the atmospheres of exoplanets to search for signs of habitability. Each new discovery, each incremental step, reminds us that the edge of possibility is always just beyond our grasp, but within our reach. Observation. The quest to explore Proxima Centauri b is emblematic of humanity's enduring drive to explore the unknown. Whether it's the voyages of Magellan, the first moon landing, or the ongoing search for extraterrestrial life, Our species is defined by its curiosity and ambition. Speculation. If we ever send a probe to Proxima Centauri b, what might it find? A barren rock scorched by stellar winds, or a world teeming with alien biology, shaped by evolutionary forces entirely different from our own? The possibilities are as diverse as they are tantalizing. Interpretation. The journey to Proxima Centauri b is not just a scientific endeavor, it is a philosophical one. It challenges us to confront our own insignificance in the cosmic scale, while celebrating our unique capacity to wonder, to dream, and to explore. In this quest, we are not just seeking new worlds, we are seeking ourselves. Part 1. The Giant Leap. How far can human ambition take us? In 1610, Galileo Galilei peered through his primitive telescope and observed Saturn's rings, a discovery that ignited centuries of astronomical exploration. His sketches, though rudimentary, laid the groundwork for future scientists to unravel the mysteries of the cosmos. Fast forward to 2016. Astronomers at the European Southern Observatory detected Proxima Centauri b, a potentially habitable exoplanet orbiting Proxima Centauri, our nearest star at just 4.24 light-years away. This discovery, made possible by the High-Accuracy Radial Velocity Planet Searcher, HARPS, spectrograph, reignited dreams of interstellar travel, a journey spanning 25 trillion miles and pushing the limits of technology and imagination. Reaching Proxima Centauri b means conquering the void. Space is not empty but filled with invisible hazards, cosmic radiation that can shred DNA, micrometeoroids traveling at hypervelocity speeds, and extreme temperatures ranging from 270 degrees Celsius in shadow to 120 degrees Celsius in sunlight. Even at the speed of light, the trip would take over 4 years. Current spacecraft, such as the Voyager probes, would require tens of thousands of years to cover the distance. This endeavor demands unprecedented innovation in propulsion, shielding, and life support. For instance, advanced propulsion systems like nuclear pulse propulsion, popularized by Project Orion in the 1950s, could theoretically achieve 3% the speed of light. But the technology remains unrealized due to political and technical barriers. Observation. Proxima Centauri b's discovery has reignited interstellar ambitions, but technology lags behind our dreams. Current chemical rockets, which rely on controlled explosions to generate thrust, are woefully insufficient for such a journey. Even advanced concepts like ion drives, which use electric fields to accelerate ions, would take thousands of years to reach Proxima Centauri b. Breakthrough Starshot, a research initiative funded by the Breakthrough Initiatives, aims to cut travel time to just 20 years by using ground-based lasers to propel tiny, lightweight spacecraft to 20% the speed of light. However, significant technical hurdles remain, including the development of materials that can withstand the intense heat and pressure of such acceleration. Proxima Centauri b orbits a red dwarf star, the most common star type in the Milky Way, accounting for over 70% of all stars. Red dwarfs are notoriously unstable, prone to violent flares that can strip away planetary atmospheres and bathe their surfaces in lethal radiation. Despite these challenges, Proxima Centauri b's existence raises profound questions about life's resilience in the cosmos. With a minimum mass of 1.17 Earth masses and an orbital period of just 11.2 days, Proxima Centauri b resides in the habitable zone, where temperatures could allow liquid water to exist on its surface. Yet, its tidal locking, where one side of the planet perpetually faces its star, presents additional obstacles for habitability, with extreme temperature variations between its day and night sides. Speculation. What awaits us at Proxima Centauri b? A barren, rocky world scarred by stellar flares, or a planet teeming with life adapted to extremes? The journey itself would transform humanity, demanding global cooperation on a scale never before seen. Confronted with the vastness of interstellar space, we would grapple with our own fragility and insignificance. From the vantage point of Proxima Centauri b, Earth would appear as a faint blue dot suspended in a cosmic sea, highlighting our shared responsibility to protect it. This perspective could unite us in ways no other challenge has, bridging divisions and inspiring collective action to safeguard our pale blue home. The dream of interstellar travel is not just about reaching distant stars. It is about pushing the boundaries of human potential. From Galileo's telescope to the detection of Proxima Centauri b, each breakthrough has expanded our vision of what is possible. This journey reflects our innate wonder, curiosity, and perseverance, offering not just new worlds to explore, but a deeper understanding of ourselves. It is a testament to our relentless drive to venture beyond the horizon, to seek answers to questions we have yet to ask, and to leave our mark on the universe. As Carl Sagan once said, somewhere, something incredible is waiting to be known. Perhaps that something lies in the red dwarf system of Proxima Centauri, beckoning us to take the giant leap. Part 2. The Blueprints of Dreams. What if the keys to interstellar travel are hidden in plain sight? Scattered across laboratories, buried in decades-old research papers and embedded in the minds of visionary scientists are the blueprints for interstellar travel. The technology we have today, ion engines, chemical rockets, and even nuclear propulsion, falls short of what is needed to traverse the abyss between stars. But the seeds of innovation are already planted, waiting to be nurtured and grown into reality. These seeds are not mere theoretical constructs, but tangible advancements, each a stepping stone toward the ultimate goal of reaching another star. Consider the ion engines used in missions like NASA's Dawn spacecraft, which launched in 2007 to explore the asteroid Vesta and the dwarf planet Ceres. These engines, which use electrically charged particles to generate thrust, are far more efficient than traditional chemical rockets. They have enabled long-duration missions with unprecedented precision, allowing Dawn to orbit and study its targets for years rather than merely fly by them. Yet despite their efficiency, ion engines lack the raw power needed for interstellar journeys. To bridge this gap, scientists are revisiting and refining concepts that were once deemed too ambitious or even dangerous. One such concept is nuclear pulse propulsion, first proposed in the late 1950s during the Cold War under the codename Project Orion. By detonating small nuclear bombs behind a spacecraft, this method could theoretically propel a vessel to speeds unimaginable with current technology. The idea, though controversial, has seen renewed interest in recent years, with designs like the pulsed fission propulsion system offering a more controlled and less environmentally hazardous approach. But nuclear propulsion is just one piece of the puzzle. The Breakthrough Starshot initiative, announced in 2016, aims to send a probe to Alpha Centauri, the closest star system to our own, using a radically different approach. The initiative proposes using a light sail propelled by ground-based lasers to accelerate a tiny spacecraft to speeds of up to 20% the speed of light. This innovative approach could make interstellar travel a reality within our lifetime, though the challenges are immense. The lasers required would need to deliver approximately 100 gigawatts of power, equivalent to the output of all the world's nuclear power plants combined. The sail itself would need to be incredibly thin and lightweight, yet durable enough to withstand the intense laser bombardment. Despite these hurdles, the initiative has already made significant progress, with prototype sails and laser systems under development. To understand the scale of the challenge, consider the distances involved. Alpha Centauri is approximately 4.37 light-years away, meaning even at 20% the speed of light, a journey would take over 20 years. This is a daunting prospect, but it is a journey that could be completed within a human lifetime, unlike the tens of thousands of years it would take with current technology. The Breakthrough Starshot initiative is not alone in its pursuit of interstellar travel. NASA's Innovative Advanced Concepts (ENIAC) program funds research into a variety of propulsion technologies, including antimatter engines and warp drives, concepts that, while still purely theoretical, offer glimpses of what might be possible in the future. One of the most intriguing proposals funded by NIAC is the use of antimatter as a propellant. Antimatter, which annihilates upon contact with normal matter, releases an enormous amount of energy, far more than any chemical or nuclear reaction. A spacecraft powered by antimatter could potentially reach relativistic speeds, approaching a significant fraction of the speed of light. However, producing and storing antimatter remains a major challenge. Current technology can produce only minuscule amounts of antimatter, and containing it requires sophisticated magnetic fields. Despite these obstacles, researchers are exploring ways to scale up antimatter production and develop more efficient storage methods. Meanwhile, the notion of warp drives, popularized by science fiction, has begun to move from the realm of speculation to serious scientific inquiry. In 1994, Mexican physicist Miguel Alcubierre proposed a theoretical model for a warp drive, which would expand space behind a spacecraft and contract space in front of it, effectively allowing the craft to move faster than light. While Alcubierre's model remains purely theoretical and faces significant practical challenges, such as the need for exotic matter with negative energy density, it has inspired further research into the manipulation of space-time. Recent studies have suggested that warp drives might be achievable with more conventional forms of energy, though the engineering hurdles remain formidable. Observation. The pursuit of interstellar travel is not a single linear path, but a web of interconnected ideas, each building on the progress of the others. Nuclear propulsion, light sails, antimatter engines, and warp drives are not competing technologies, but complementary approaches, each offering a glimpse into the possibilities of human ingenuity. Speculation. As these technologies advance, they may converge in unexpected ways, creating hybrid systems that combine the strengths of multiple approaches. For example, a spacecraft might use nuclear propulsion to escape the solar system, then deploy a light sail to accelerate to near light speeds, and finally activate an antimatter engine for the final push into interstellar space. The future of interstellar travel may lie not in a single breakthrough, but in the integration of many. The blueprints of interstellar travel are not static documents, but living, evolving ideas, shaped by the relentless curiosity and innovation of scientists and engineers. Each breakthrough brings us one step closer to transcending the boundaries of our solar system and venturing into the vast, unexplored expanse of the cosmos. The journey will be long and fraught with challenges, but the promise of what lies beyond is a beacon that guides us forward. The stars are not just distant points of light, but destinations within our reach, and the blueprints to get there are already taking shape. Part 3. The Limits of Knowledge. How close are we to unraveling the mysteries of the cosmos? The answer lies in a delicate balance between our technological prowess and the vast, unyielding expanse of the universe. Every breakthrough we celebrate is accompanied by a humbling reminder of how much remains unknown. The search for habitable planets beyond our solar system has yielded remarkable discoveries, but it has also revealed the vastness of our ignorance. Exoplanets like Proxima Centauri b, a potentially Earth-like world orbiting our nearest stellar neighbor, and Gliese 121b, a super-Earth in the constellation Ophiuchus, hint at the possibility of worlds where life could thrive. Yet, the data we have is frustratingly incomplete. These planets are mere silhouettes against the stars, their surfaces and atmospheres obscured by distance and the limitations of our instruments. To truly understand these distant worlds, we must first master the art of observation. Astronomy has always been a science of patience and precision. The radial velocity method, which detects subtle fluctuations in a star's motion caused by the gravitational pull of an orbiting planet, has been instrumental in identifying exoplanets. Over the past 3 decades, this technique has helped confirm the existence of over 1,000 exoplanets, including the first known exoplanet, 51 Pegasi b, discovered in 1995. But this method has its limitations. It favors the detection of massive planets in close orbits, so-called hot Jupiters, while smaller, Earth-like planets in wider orbits remain elusive. To fully understand the conditions on these worlds, we need to study their atmospheres, their geology, and their potential for liquid water. This is where telescopes like the James Webb Space Telescope, JWST, come into play. Launched in December 2021, the JWST represents the pinnacle of human ingenuity in space exploration. With its 6.5-meter gold-coated mirror and advanced infrared detectors, it is designed to peer into the farthest reaches of the cosmos, studying everything from the first galaxies to the atmospheres of exoplanets. Using transmission spectroscopy, JWST can analyze the light passing through an exoplanet's atmosphere during transit, revealing the presence of key molecules like water vapor, oxygen, and methane. These biosignatures are the chemical fingerprints of life, offering clues to the potential habitability of distant worlds. But even JWST has its constraints. Its sensitivity is limited by the faintness of exoplanet signals and the need to differentiate between molecular signatures and instrumental noise. Observation. The first exoplanet atmosphere studied by JWST was that of WASP-39b, a gas giant approximately the size of Saturn. The telescope detected clear evidence of water vapor, carbon dioxide, and sulfur dioxide, a tantalizing glimpse into the chemistry of another world. However, WASP-39b is not a habitable planet. It is a scorching world with temperatures exceeding 800 degrees Celsius. To find biosignatures on potentially habitable exoplanets, JWST will need to focus on smaller, cooler planets, which are far more challenging to observe. The search for life beyond Earth is not just a scientific endeavor, it is a philosophical quest to understand our place in the universe. Yet the limits of our knowledge are daunting. Consider the sheer scale of the cosmos. The Milky Way galaxy alone contains an estimated 100 to 400 billion stars, and there are roughly 2 trillion galaxies in the observable universe. Even if we assume that just 1% of stars host potentially habitable planets, the number of worlds to explore is astronomical. Adding to this challenge is the fact that our current methods of detection are biased toward planets with short orbital periods, as these are easier to observe. Planets with longer orbits, like Earth's 365-day journey around the Sun, remain hidden from our view. Interpretation. The Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the Milky Way. While the equation is highly speculative, it underscores the immense uncertainties involved in the search for extraterrestrial life. Factors such as the average number of planets per star, the fraction of those planets that could support life, and the likelihood of life evolving into intelligent civilizations are all unknowns. Even the most optimistic estimates suggest that the nearest such civilization could be thousands of light years away, far beyond our current technological reach. Despite these limitations, the quest for knowledge continues. The Next Generation Transit Survey, NGTS, a ground-based array of telescopes in Chile, is designed to detect exoplanets by monitoring the subtle dips in starlight caused by transiting planets. Since its first light in 2015, NGTS has discovered dozens of exoplanets, including NGTS-1b, a gas giant in a tight orbit around a small, cool star. This discovery demonstrated that even small telescopes can make significant contributions to exoplanet research, complementing the work of larger observatories like JWST. Speculation. What if the first signs of extraterrestrial life are not found on an Earth-like planet, but in the unexpected chemistry of a gas giant or the subsurface ocean of an icy moon? Scientists are increasingly turning their attention to worlds like Jupiter's moon Europa and Saturn's moon Enceladus, both of which harbour vast oceans beneath their frozen surfaces. These moons are not habitable in the traditional sense, but they offer intriguing possibilities for life to exist in environments far removed from our own. The upcoming Europa Clipper mission, scheduled to launch in 2024, will conduct multiple flybys of Europa to study its ocean and search for signs of habitability. The limits of our knowledge are not static. They are ever-shifting boundaries that recede with each new discovery. Yet the universe is vast, and our understanding of it is still in its infancy. Every exoplanet we detect, every molecule we identify in an alien atmosphere, brings us one step closer to answering the ultimate question. Are we alone? But for now, the cosmos remains a vast, enigmatic puzzle, challenging us to push the boundaries of what we know and what we can imagine. Part 4. The Cosmic Haystack. How do we find a needle in the vast expanse of the universe? The scale of the search is almost incomprehensible. The observable universe stretches across 93 billion light-years, containing an estimated 2 trillion galaxies, each with hundreds of billions of stars on average. Among these countless stars, astronomers have identified approximately 5,000 exoplanets in our own Milky Way galaxy alone, with tens of billions more predicted to exist. The task is akin to searching for a single grain of sand on all the beaches of Earth. The search for extraterrestrial life is not just about finding planets. It's about understanding the conditions that make life possible. Biosignatures like oxygen, ozone, and methane are the starting point, but they are not the whole story. Oxygen, for instance, is produced by photosynthesis on Earth and is responsible for the great deoxygenation event some 2.4 billion years ago, which allowed aerobic organisms to thrive. Similarly, methane is produced by microbes in environments like hydrothermal vents, where life on Earth may have first emerged. But these biosignatures can also be produced by abiotic processes, such as volcanic activity or chemical reactions in a planet's atmosphere. To truly grasp the potential for life beyond Earth, we must look for technosignatures, evidence of advanced civilizations that have harnessed technology to alter their environments. Projects like Breakthrough Listen are scouring the cosmos for these technosignatures, using vast networks of radio telescopes to detect signals that could indicate the presence of intelligent life. Breakthrough Listen, launched in 2015, is the most comprehensive search for extraterrestrial intelligence, SETI, ever undertaken, with a $100 million budget and access to some of the world's most powerful telescopes. The project targets the closest 1 million stars, the entire galactic plane, and 100 nearby galaxies, scanning billions of radio frequencies for signs of artificial transmission. But the search is fraught with challenges. The cosmos is a noisy place, filled with natural phenomena that can mimic the signals we seek. For example, pulsars, rapidly spinning neutron stars, emit regular radio pulses that were initially mistaken for extraterrestrial signals in the 1960s. Distinguishing a true technosignature from background noise is a monumental task, but it is one that scientists are tackling head-on. One of the greatest challenges in the search for technosignatures is the sheer volume of data. Breakthrough. Listen collects petabytes of information daily, more than the entire contents of the Library of Congress. To process this deluge, researchers are turning to artificial intelligence and machine learning algorithms, which can sift through the data faster and more accurately than humans. These algorithms are trained to recognize patterns and anomalies, identifying potential signals that warrant further investigation. Yet even with these advanced tools, the search is painstaking. A single false positive can send researchers down a rabbit hole of analysis, only to discover that the signal was a glitch or interference from Earth-based technology. Despite the challenges, the search for technosignatures has yielded intriguing results. In 2020, Breakthrough Listen detected a mysterious radio signal from Proxima Centauri, the closest star to our solar system. The signal, dubbed BLC1, had a frequency of 980 MHz and appeared to shift in a way that suggested it was not natural. Though further analysis eventually ruled out an extraterrestrial origin, the discovery highlighted the potential of the search and the need for rigorous follow-up. Other unexplained signals, such as the WOW signal detected in 1977, remain unsolved, tantalizing reminders of what might be out there. As we sift through the data, we are not just searching for signals, we are searching for meaning. Each potential signal is a piece of the cosmic puzzle, a clue that brings us one step closer to understanding our place in the universe. The search for extraterrestrial life is, at its core, a quest to answer one of humanity's most profound questions. Are we alone? This question drives not only scientific inquiry, but also philosophical and existential reflection. It forces us to confront our own insignificance in the cosmic scheme and to wonder about the nature of intelligence, consciousness, and the purpose of existence itself. Observation. The universe is silent in the ways we expect it to be. Despite decades of listening, we have yet to detect a clear, unambiguous signal from an extraterrestrial civilization. This silence, often referred to as the Great Silence, raises fundamental questions about the prevalence of intelligent life and the longevity of advanced civilizations. Interpretation. The absence of evidence is not evidence of absence. The Great Silence could be explained by a variety of factors, including the rarity of life, the short lifespans of civilizations, or the possibility that advanced beings have chosen to remain hidden. Alternatively, it could be that our search methods are flawed, and we are looking in the wrong places or for the wrong signs. Speculation. Perhaps extraterrestrial civilizations have already visited Earth, leaving behind artifacts or evidence that we have yet to recognize. Or maybe they exist in forms so alien that we cannot comprehend their presence. Some theories even suggest that advanced civilizations might transcend the physical realm entirely, existing as pure energy or information in dimensions beyond our perception. As we continue to scan the cosmic haystack, we are driven by both curiosity and hope. Curiosity about the nature of life and intelligence, and hope that we are not alone in the universe. The search for extraterrestrial life is a testament to human ingenuity and resilience, a testament to our unyielding desire to explore the unknown. And while the universe may be vast and the odds daunting, the quest itself is a reminder of what makes us human, our insatiable hunger for knowledge and connection. Part 5. The Edge of the Solar System. What secrets lie beyond the familiar boundaries of our cosmic neighborhood? The edge of the solar system is a realm of profound mystery and astonishing discovery, where the familiar gives way to the enigmatic. Here, the sun's influence wanes, and the environment becomes increasingly hostile to human exploration. Yet, it is in this distant frontier that some of the most intriguing questions about our solar system's origins and evolution await answers. Beyond the gas giants and the asteroid belt lies a world shrouded in mystery, Neptune. For decades we have imagined it as a dark blue sphere at the edge of our solar system, but recent discoveries have revealed a reality far more complex. Neptune's true colors, hidden beneath a shroud of methane, are a testament to the limits of human perception and the power of scientific inquiry. At 4.5 billion kilometers from the Sun, Neptune receives only 0.1% of the sunlight that Earth does, making it one of the coldest and darkest planets in our solar system. Its average surface temperature hovers around 217 degrees Celsius, a stark reminder of the extremes that define this distant world. In 1989, the Voyager 2 spacecraft captured the first close-up images of Neptune, revealing a world of storms and dynamic weather patterns. But these images were just the beginning. Recent studies have shown that Neptune's color is not a deep blue, but a more muted shade, the result of complex interactions between methane and other atmospheric components. This discovery has forced us to rethink our understanding of the ice giant and its place in the solar system. The methane in Neptune's atmosphere absorbs red light and scatters blue light, creating the planet's distinctive hue. However, additional compounds such as hydrogen sulfide contribute to the subtle variations in its color, hinting at a more intricate atmospheric chemistry than previously thought. But Neptune is more than just a color. It is a window into the past. Its atmosphere, filled with storms and mysteries, offers clues to the conditions that shaped the outer solar system. From the great dark spot, a storm larger than Earth, to the enigmatic hotspots that defy explanation, Neptune is a world of extremes. Understanding its dynamics could shed light on the formation and evolution of ice giants throughout the galaxy. The Great Dark Spot, first observed by Voyager 2, was a massive anticyclonic storm system, comparable in size to the Great Red Spot of Jupiter. However, unlike Jupiter's storm, Neptune's Great Dark Spot disappeared within a few years, highlighting the planet's rapid and unpredictable weather patterns. Observation. Neptune's magnetic field is another source of fascination. Tilted at an angle of 47 degrees relative to its rotational axis, the magnetic field is strongly offset from the planet's center, creating a complex and asymmetric magnetosphere. This unique configuration challenges our understanding of planetary magnetic fields and suggests that Neptune's interior dynamics are far more chaotic than those of other planets. The auroras produced by this magnetic field are faint and diffuse, visible only through specialized instruments, yet they paint a mesmerizing picture of the planet's interaction with the solar wind. Interpretation. The behavior of Neptune's moons, particularly Triton, adds another layer of intrigue. Triton is the only large moon in the solar system with a retrograde orbit, meaning it orbits in the opposite direction to Neptune's rotation. This suggests that Triton was likely captured from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Triton's surface is one of the coldest in the solar system, with temperatures as low as 235 degrees Celsius. Its thin nitrogen atmosphere supports the formation of geysers, which erupt plumes of nitrogen gas and dust up to 8 kilometers into the sky. These geysers are powered by the sublimation of nitrogen ice, driven by the faint warmth of the distant sun. Speculation. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies that extends from 30 to 55 astronomical units, AU, from the Sun. This belt is home to thousands of known objects, including Pluto, Eris, and Sedna, and it is estimated to contain hundreds of thousands more. The Kuiper Belt is a remnant of the early solar system, a frozen time capsule of the materials that formed the planets. Studying its objects could provide critical insights into the composition and dynamics of the primordial solar nebula, the swirling disk of gas and dust from which the sun and planets coalesced. The New Horizons spacecraft, which flew past Pluto in 2015, offered the first close-up views of a Kuiper Belt object. Pluto's icy surface revealed a complex geology, with towering mountains of water ice, vast glaciers of frozen nitrogen, and a thin atmosphere composed mostly of nitrogen, methane, and carbon monoxide. The heart-shaped region known as Tombor Regio, named after Pluto's discoverer Clyde Tombaugh, is a vast, smooth plain devoid of craters, suggesting recent geological activity. This discovery challenged the long-held assumption that small, icy worlds in the outer solar system were geologically inactive. The edge of the solar system is not a static boundary, but a dynamic frontier. As we push the limits of exploration, we uncover worlds that defy our expectations and expand our understanding of the cosmos. Neptune, with its storms, magnetic oddities, and enigmatic moons, stands as a testament to the wonders that await us in the farthest reaches of our celestial neighborhood. The journey to the edge of the solar system is not just a quest for knowledge, It is a voyage into the unknown, a chance to redefine what it means to exist on the boundary of human experience. Part 6. The Icy Frontier. What lies beneath the frozen surface of Pluto? Once considered the ninth planet, Pluto has been reclassified as a dwarf planet, but its significance remains undiminished. Its demotion in 2006 by the International Astronomical Union sparked controversy, yet it did little to dampen scientific curiosity. In 2015, the New Horizons spacecraft, launched 9 years earlier, completed its 9-year, 3 billion-mile journey, flying past Pluto at a speed of over 30,000 miles per hour. This fleeting encounter lasted mere hours, but revealed a world of towering ice mountains soaring up to 11,000 feet, nitrogen glaciers that slowly flow like frozen rivers, and a heart-shaped region known as Sputnik Planitia, stretching over 600 miles across. These discoveries have transformed our understanding of the outer solar system and the potential for life beyond Earth. Pluto's thin atmosphere, composed primarily of nitrogen, methane, and carbon monoxide, extends far beyond its surface, interacting with solar wind particles and creating a dynamic, ever-changing environment. Pluto's icy surface hides a dynamic interior. The presence of Sputnik Planitia, a vast basin filled with nitrogen ice, suggests that the dwarf planet may harbor a subsurface ocean. This ocean, if it exists, could span a depth of up to 60 miles and is likely sustained by the decay of radioactive elements in Pluto's rocky core. This subsurface environment, insulated from the frigid temperatures of the surface, which plummet to 388 degrees Fahrenheit, could be a haven for life, protected from the harsh conditions above. The possibility of liquid water beneath Pluto's frozen crust raises intriguing questions about the potential for habitability in the outer reaches of the solar system. It also challenges our assumptions about where life might emerge, pushing the boundaries of astrobiology. The interaction between Pluto's atmosphere and its surface also hints at ongoing geological activity, with methane frosts and haze particles continually reshaping its landscape. But Pluto is not alone. Its largest moon, Charon, is a world in its own right, with deep canyons plunging up to 6 miles deep and towering mountains that hint at a complex geological history. Charon, roughly half the size of Pluto, is the largest moon relative to its parent body in the solar system, forming a binary system where both bodies orbit a common center of mass. This interaction between Pluto and Charon is a gravitational ballet, a dance of celestial bodies that challenges our understanding of planetary dynamics. The New Horizons mission revealed that Charon, too, has a surprising diversity of terrain, including a polar cap of reddish material, likely tholins, complex organic molecules formed by the interaction of ultraviolet radiation and methane. This discovery raises questions about the potential for organic chemistry, a precursor to life, in the frigid outer solar system. Charon's icy surface may also contain traces of cryovolcanic activity, where water ice slurries erupt from beneath its crust, reshaping its terrain over billions of years. Beyond Pluto and Charon, the Kuiper Belt, a vast region of icy bodies beyond Neptune, stretches into the cosmic void. This icy frontier is home to countless objects, including Arrokoth, a snowman-shaped body visited by New Horizons in 2019. Arrokoth, a pristine relic from the early solar system, offers clues about the formation of planets and the building blocks of life. Its 2 lobes, joined by a narrow neck, suggest it formed from the gentle collision of two smaller bodies, preserving a record of the solar system's infancy. The Kuiper Belt, with its trillions of icy bodies, may hold the key to understanding how water and organic materials were delivered to Earth billions of years ago, seeding the conditions for life to emerge. The Kuiper Belt's objects, including larger members like Eris and Haumea, exhibit diverse compositions and histories, providing a rich tapestry of clues about the solar system's evolution. Yet the icy frontier is not limited to the Kuiper Belt. Farther out lies the Oort cloud, a theoretical spherical shell of icy bodies that may extend up to 1 light-year from the Sun. This distant reservoir of comets is believed to be the source of long-period comets that occasionally venture into the inner solar system. These comets, like time capsules from the solar system's birth, carry water, organic compounds, and other materials that could have contributed to the emergence of life on Earth. The study of these icy wanderers offers a glimpse into the conditions of the early solar system and the processes that shaped our cosmic neighborhood. The Oort cloud, though difficult to observe directly, is thought to contain billions of comets, each a frozen remnant of the solar system's chaotic beginnings. As we explore these distant worlds, we are not just uncovering the secrets of the solar system, we are redefining the boundaries of what is possible. The icy frontier, from Pluto's subsurface ocean to the pristine bodies of the Kuiper Belt, challenges our understanding of habitability and the potential for life beyond Earth. Each discovery pushes the frontier of knowledge further, inspiring new questions and igniting the human urge to explore the unknown. In this vast expanse of ice and mystery, we find not only the limits of our solar system, but the limitless potential of the cosmos itself. The search for life, whether microbial or more complex, drives our exploration of these distant realms, as scientists and engineers work to develop technologies capable of probing deeper into the cosmic abyss. The icy frontier also presents practical challenges for future exploration. The vast distances and extreme conditions require innovative solutions, from advanced propulsion systems to robotic probes capable of surviving the frigid temperatures and low light conditions. Yet the rewards are immense. Every new mission to this region, whether to Pluto, the Kuiper Belt, or even the distant Oort cloud, promises to unlock new insights into the origins of our solar system and the potential for life beyond Earth. As we push further into the unknown, we not only expand our scientific understanding, but also inspire future generations to dream of the possibilities that lie hidden in the icy depths of the cosmos. Observation. The New Horizons mission has revolutionized our understanding of Pluto and its moons, revealing a world far more dynamic and complex than previously imagined. Its discoveries in the Kuiper Belt, including Arakoth, have provided critical insights into the early solar system. Interpretation. The presence of subsurface oceans on Pluto and potentially other Kuiper Belt objects suggests that liquid water, a key ingredient for life as we know it, may be more common in the outer solar system than once thought. This challenges traditional views of habitability and expands the search for life to more distant and unexpected locations. Speculation. If future missions confirm the existence of subsurface oceans on Pluto or other icy bodies, the next question will be whether these environments could support life. Could microbial ecosystems thrive in the dark, frigid waters beneath the ice? And if so, how would such life compare to what we find on Earth? The answers to these questions could redefine our understanding of life's potential in the cosmos. Part 7. The red planet's secrets. What stories are written in the sands of Mars? Mars has long captivated the human imagination, a world of ancient rivers, towering dust devils, and a thin, fragile atmosphere. But beneath its reddish surface lies a canvas of geological mysteries, from the enigmatic brain terrain to the traces of ancient water streams. These features are not just relics of the past, they are clues to the planet's climatic history and the potential for life. The red planet, named for the Roman god of war, has been studied extensively since the dawn of space exploration. Over 50 spacecraft have been launched to Mars, with various missions focused on unraveling its secrets. Among these, the Mars Reconnaissance Orbiter, MRO, has provided unprecedented detail, capturing images of the Martian surface with resolutions as fine as 25 centimeters per pixel, revealing intricate textures and formations invisible to previous missions. The brain terrain, with its intricate patterns reminiscent of the human brain, is a geological marvel that defies explanation. Scientists suspect that sublimation, the process by which ice transitions directly to vapor, plays a key role in its formation. But the exact mechanisms remain elusive, a puzzle waiting to be solved. These labyrinthine structures, which span hundreds of meters in diameter, are often found in the planet's polar regions, where temperatures can plunge to 155 to 243 degrees. The interplay between ice, dust, and wind in these harsh environments creates a dynamic landscape where features shift and evolve over time. Observational data from the Mars Express mission, launched in 2003, has provided critical insights into these processes, highlighting how the interplay of water ice and carbon dioxide ice shapes the terrain. Beyond the brain terrain, Mars is a world of extremes. Its atmosphere, though thin, is home to colossal storms and unusual hotspots that defy conventional wisdom. These phenomena are not just curiosities, they are windows into the planet's internal dynamics and the forces that shape its surface. For instance, global dust storms on Mars can envelop the entire planet, blocking sunlight and dramatically altering surface temperatures. These storms, which occur approximately every 3 Martian years, about 5.5 Earth years, can last for months, transforming the planet into a hazy, orange-tinted sphere. The most recent global dust storm observed in 2018 grounded NASA's Opportunity rover, which relied on solar power to operate. Despite the mission's end, the storm provided invaluable data on the atmospheric dynamics of Mars, including the role of wind patterns and thermal gradients in driving these events. The planet's polar ice caps are another testament to its dynamic nature. The northern cap, composed primarily of water ice, has a diameter of about 1,000 kilometers during the Martian summer, while the southern cap, which contains both water ice and frozen carbon dioxide, spans roughly 400 kilometers. These caps undergo dramatic seasonal changes, expanding and contracting with the planet's orbital cycle. Intriguingly, the layers within the polar ice caps preserve a geological record of Mars's climate history, stretching back millions of years. The Mars Ice Mapper mission, slated for launch in the coming decade, aims to study these layers in detail, using ground-penetrating radar to map the composition and structure of the ice. Scientists hope this data will shed light on past climatic shifts, including periods when Mars may have been warm enough to support liquid water on its surface. Yet, the most tantalizing features of Mars are the remnants of ancient rivers and lakes, which hint at a warmer, wetter past. The Curiosity rover, which landed in Gale Crater in 2012, has discovered extensive evidence of ancient water activity, including rounded pebbles and sedimentary deposits that suggest the presence of flowing streams. These findings are supported by orbital data which reveal networks of dried-up riverbeds and delta formations across the Martian surface. One of the most striking examples is the Jezero crater, the landing site of NASA's Perseverance rover. This crater, once a lake fed by a river, contains fan-shaped deposits that scientists believe were formed by sediment carried by water. The Perseverance rover is currently collecting samples from these deposits, which will be returned to Earth in the coming years, offering a chance to study Martian geology and potential biosignatures in terrestrial laboratories. The search for life on Mars, whether past or present, is intertwined with the planet's geological history. The presence of methane in the Martian atmosphere, detected by both the Curiosity rover and the Mars Express orbiter, is a particularly intriguing clue. Methane can be produced by geological processes, such as the interaction of water and certain minerals, but it can also be a byproduct of microbial life. The concentrations of methane on Mars fluctuate seasonally, suggesting active processes at work. The Mars 2020 Perseverance rover is equipped with instruments designed to analyze the chemical composition of Martian rocks and soils, searching for organic compounds and other signs of past microbial activity. Additionally, the rover carries the MOXIE experiment, which aims to produce oxygen from the Martian atmosphere, paving the way for future human exploration and habitation. As we delve deeper into the mysteries of Mars, we are not just exploring a distant world. We are uncovering the story of our own planetary origins. The red planet's geology, climate, and potential for life offer a mirror through which we can better understand the processes that shaped Earth. By studying Mars, we gain insights into the conditions that may have allowed life to emerge on our own planet, as well as the factors that influence habitability beyond Earth. The ongoing exploration of Mars, from rovers on the surface to orbiters above, represents a collective human endeavor to push the boundaries of knowledge and discovery. With each new mission, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? To Part 8. The Moon's Hidden Treasures. The Moon's south pole, a region cloaked in perpetual darkness, holds secrets untouched for billions of years. Unlike the familiar face of the Moon, this area is marked by stark contrasts, with temperatures plummeting to 382 degrees Fahrenheit. It is a world of eternal twilight, where sunlight barely grazes the surface, and mysteries lie locked in the frozen soil. The terrain here is unlike anywhere else on the Moon, with towering peaks that stand in eternal sunlight, just kilometers away from craters that haven't seen a ray of light in over 2 billion years. These shadowed regions, known as permanently shadowed regions, PSRs, are estimated to cover approximately 2,600 square kilometers and hold some of the coldest temperatures ever recorded in the solar system. In 2023, India's Chandrayaan-3 mission sought to explore this alien landscape, aiming for the rim of Shackleton Crater, a 13-mile-wide impact site. This crater, named after Ernest Shackleton, is one of the coldest places in the solar system, yet promises unprecedented scientific discoveries. The mission aimed to achieve a soft landing, a first for the lunar South Pole. Scientists guided the Vikram lander through treacherous terrain, seeking to demonstrate India's space exploration capabilities and pave the way for future missions. The lander carried a suite of instruments, including a seismometer to study moonquakes and a spectrometer to analyze the composition of the lunar soil. The Chandrayaan-3 rover, Pragyan, was equipped with tools to measure the chemical makeup of the regolith, providing insights into the moon's geological past. Chandrayaan-3's instruments revealed a surface rich in sulfur, aluminum, calcium, and iron, hinting at a complex geological history. The lander also detected seismic activity, challenging the belief that the moon is geologically inactive. These moonquakes, varying in intensity and origin, offer clues to the moon's formation and evolution. The seismic data suggested that the moon's interior may still harbor a partially molten core, which could explain the observed tectonic activity. Additionally, the mission discovered evidence of ancient volcanic activity, with lava flows dating back billions of years, suggesting a once active geological past. Observation. The seismic activity aligns with NASA's Apollo mission data, which detected thousands of moonquakes. Deep quakes suggest the moon's interior may still be partially molten, driving tectonic processes. The Apollo missions, particularly Apollo 17 in 1972, left seismometers on the lunar surface that recorded over 2,000 moonquakes during their operation. These quakes were categorized into 4 types: shallow, deep, thermal, and impact-related. The deep quakes, originating from about 700 kilometers below the surface, indicate ongoing activity within the moon's mantle. Interpretation. If the moon is tectonically active, its core may still generate heat, explaining the presence of water ice in shadowed craters. Volcanic activity or outgassing could have contributed to these deposits. The moon's mantle, rich in radioactive elements like uranium and thorium, may produce enough heat to keep parts of the core molten. This heat could drive convection currents in the mantle, causing the moon to contract and expand, resulting in moonquakes. Speculation. An active lunar interior raises possibilities for geothermal energy sources, potentially powering lunar bases or extracting water from ice deposits. This could shape future lunar exploration, transforming the moon into a vital resource for space travel. Geothermal energy on the moon could provide a reliable power source for habitats, rovers, and scientific instruments. Additionally, the heat could be used to extract water from ice deposits, making it a renewable resource for life support and fuel production. Beyond geological mysteries, the South Pole holds the promise of water ice, hidden in permanently shadowed craters. These deposits, untouched by sunlight for billions of years, could contain hundreds of millions of tons of water. If extracted, this resource could support sustainable lunar habitation, reducing future mission costs and enabling longer stays. Scientists estimate that the lunar South Pole may hold up to 600 million metric tons of water ice, enough to fill over 240,000 Olympic-sized swimming pools. This ice is believed to have originated from comets and asteroids that impacted the moon over billions of years, depositing water that became trapped in the PSRs. Extracting water ice poses significant challenges due to extreme temperatures. However, advancements in robotic technology, like NASA's Viper rover, offer innovative solutions. Mapping water ice deposits and developing extraction methods could turn the moon into a refueling station for deep space missions. The Viper rover, scheduled to land in 2024, will use its neutron spectrometer to detect hydrogen, a key indicator of water ice, up to 1 meter below the surface. Its drill will extract samples from these deposits, providing critical data on their composition and accessibility. The Moon's treasures extend beyond water ice. The South Pole is rich in helium-3, a rare isotope deposited by the solar wind. This potential fuel for nuclear fusion reactors could revolutionize energy production on Earth, offering a clean and sustainable alternative. Helium-3 is a non-radioactive isotope of helium that could be used in fusion reactions to generate energy without producing radioactive waste. Unlike hydrogen-based fusion, helium-3 reactions release more energy and are easier to control, making them a promising candidate for future power generation. Observation. The Moon holds an estimated 1 million tons of helium-3. However, extracting it requires advanced techniques due to its low concentration in the lunar regolith. Helium-3 is embedded in the top layer of the lunar soil, deposited over billions of years by the solar wind. Its concentration varies across the Moon's surface, with higher amounts found in regions exposed to more solar wind, such as the lunar poles. Interpretation. While technical hurdles exist, helium-3 could meet global energy demands for centuries. Fusion technology, still in early development, could make helium-3 a practical energy source in the future. Researchers are currently working on ways to efficiently extract helium-3 from the lunar regolith, with methods such as heating the soil to release the gas being explored. Once extracted, the helium-3 could be transported to Earth for use in fusion reactors, providing a nearly limitless source of clean energy. Speculation. Lunar helium-3 mining could drive innovation in robotics and energy production, turning the Moon into a hub of industrial activity. This could support a new era of space-based industries and settlements. The development of helium-3 extraction technology could lead to the establishment of lunar mining operations, creating jobs and economic opportunities in space. Additionally, the infrastructure built to support these operations could pave the way for permanent human settlements on the Moon. The Moon's South Pole is more than a scientific curiosity. It is a gateway to the future. Its hidden treasures, water ice, helium-3, and geological secrets are the building blocks of a new era in space exploration. Though challenges remain, the rewards are immense. Each mission and discovery brings us closer to unlocking the Moon's potential, making it a tangible part of our future. The upcoming Artemis program, led by NASA, aims to land the first woman and the next man on the lunar South Pole by 2025, marking the beginning of a sustained human presence on the Moon. This program, along with international collaborations, will lay the groundwork for future lunar habitats, resource extraction, and scientific research, ushering in a new age of lunar exploration. Part 9. The Fires of Creation. What can supernovae tell us about the birth of stars and planets? Supernovae are not just cosmic spectacles, they are the engines of creation, forging the elements that make up planets, stars, and even life itself. These cataclysmic explosions mark the end of a massive star's life, but they are also the beginning of something new. From the ashes of a supernova, new stars are born, and the cycle of creation continues. Supernovae can release as much energy in a single burst as the Sun will produce over its entire 10 billion-year lifespan, making them one of the most powerful events in the universe. The shock waves from these explosions can trigger the collapse of nearby molecular clouds, sparking the formation of new stars and planetary systems. Betelgeuse, a red supergiant in the constellation Orion, is a prime example of this cosmic drama. Recent observations have shown that Betelgeuse is nearing the end of its life, its outer layers pulsating with the rhythm of a dying star. When it finally explodes, it will release an enormous amount of energy, briefly outshining the entire Milky Way galaxy. This explosion will not only be a spectacle, it will be a testament to the power of stellar evolution. Betelgeuse, located approximately 640 light-years from Earth, is one of the largest stars visible to the naked eye, with a diameter roughly 1,200 times that of the Sun. Its impending supernova will scatter heavy elements across the cosmos, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. Observation: the dimming of Betelgeuse in late 2019 and early 2020 was initially thought to signal its imminent collapse, but further analysis revealed it was likely due to a combination of dust obscuration and changes in its surface temperature. This event highlighted the challenges of predicting the exact moment of a supernova, even for well-studied stars. But supernovae are more than just explosions. They are the crucibles of the cosmos. The elements forged in their fiery depths, carbon, oxygen, iron, are the building blocks of life. By studying these stellar explosions, we are not just witnessing the death of stars, we are witnessing the birth of worlds. Supernovae are responsible for the creation of elements heavier than hydrogen and helium, which make up the bulk of the periodic table. For instance, the calcium in our bones, the iron in our blood, and the gold in our jewelry were all forged in the hearts of stars and scattered by supernova explosions billions of years ago. The Crab Nebula, the remnant of a supernova observed in 1054 AD, is a stunning example of this process. Located in the constellation Taurus, it is a sprawling cloud of gas and dust, still glowing with the energy of its progenitor star's explosion. At its center lies a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. The Crab Nebula is just one of many supernova remnants that dot the galaxy, each a testament to the creative power of these explosions. These remnants often span dozens of light years and contain filaments of gas heated to millions of degrees, emitting X-rays that can be detected by telescopes like NASA's Chandra X-ray Observatory. Interpretation: supernova remnants are not just relics of past explosions, they are active laboratories for studying the physics of shockwaves, magnetic fields, and particle acceleration. The energy released by a supernova can accelerate particles to nearly the speed of light, creating cosmic rays that bombard the Earth's atmosphere and contribute to the background radiation of the universe. One of the most intriguing aspects of supernovae is their role in the formation of the solar system. Approximately 4.6 billion years ago, a nearby supernova may have triggered the collapse of the molecular cloud that gave birth to our Sun and its planets. This explosion would have seeded the cloud with heavy elements, enriching it with the raw materials needed to form rocky planets like Earth. The isotopic signatures found in meteorites and lunar rocks suggest that at least one nearby supernova contributed to the composition of the early solar system. Speculation: could life on Earth owe its existence to a supernova? The heavy elements forged in these explosions are essential for biological processes. Iron, for example, is a key component of hemoglobin, the protein that carries oxygen in our blood. Without supernovae, the universe would be a far less diverse and complex place. The study of supernovae is not just about understanding the past, it is about shaping our future. By observing these explosions in distant galaxies, astronomers can measure the expansion of the universe and probe the nature of dark energy. Supernovae also serve as cosmic clocks, helping us map the timeline of the universe's evolution. The more we learn about these stellar fires, the closer we come to unlocking the mysteries of creation itself. Part 10. The Ghost in the Machine. Is there an undiscovered planet hiding in the outer reaches of our solar system? This question fuels our exploration of the unknown. For centuries, astronomers have charted the heavens, but the farthest regions of our solar system remain shrouded in mystery. Every new observation adds a piece to the cosmic puzzle, yet the full picture remains tantalizingly out of reach. Beyond the Kuiper Belt, a mysterious force seems to tug at the orbits of distant objects. This unseen presence, dubbed Planet 9, is hypothesized from the gravitational interactions that affect the paths of trans-Neptunian objects. These icy bodies hint at a hidden world through their perturbed trajectories. The orbits of at least 6 Kuiper Belt objects appear to cluster in ways that defy explanation without the influence of an unseen mass. The Kuiper Belt, located 30 to 55 astronomical units (AU) from the Sun, contains thousands of icy bodies, including Pluto. However, objects like Sedna and 2012 VP-113 have orbits that defy the known planet's gravitational influence. In 2016, Caltech scientists proposed that Planet 9, if it exists, would be 10 times Earth's mass and orbit at an average distance of 700 AU, 20 times farther than Neptune. Such a world would experience temperatures as low as 220 degrees. The search for Planet 9 raises questions about exotic possibilities like primordial black holes or dark matter clumps. The Subaru telescope in Hawaii has scanned vast swaths of the night sky, detecting over 800 trans-Neptunian objects since 1998. Each discovery adds to the statistical evidence supporting or refuting Planet 9's existence. Planet 9, if confirmed, would test the limits of our scientific understanding. Its discovery would build on revelations like the complexity of the Kuiper Belt, discovered in the 1990s. Planet 9 could further reshape our cosmic horizons, challenging our ideas about the solar system's boundaries and evolution. Its orbit, if confirmed, would take between 10,000 and 20,000 years to complete. Observation: the pursuit of Planet 9 has reignited interest in the outer solar system. The New Horizons spacecraft, which flew past Pluto in 2015, provided the first close-up images of a Kuiper Belt object. Its next target, Arrokoth, offered unprecedented insights into the early solar system. These discoveries hint at a cosmic treasure trove waiting to be explored. This quest has also spurred technological innovation. Telescopes like the Subaru in Hawaii and the upcoming Vera C. Rubin Observatory in Chile are revolutionizing our ability to detect faint, distant objects. The Rubin Observatory, set to begin operations in 2024, will image the entire visible sky every 3 nights, generating a staggering 20 terabytes of data per night. Speculation. If found, Planet 9 could offer unprecedented insights into the solar system's early history. It may have been ejected to its distant orbit by interactions with gas giants like Jupiter and Saturn, or it could be a captured rogue planet from another star system. The possibility of a captured world challenges our understanding of gravitational interactions between stars and the potential for interstellar exchange. Planet Nine's implications extend beyond our solar system, challenging models of planetary formation. Its existence would force astronomers to rethink the processes shaping planetary systems across the universe. Recent studies suggest that as many as 50% of stars in the Milky Way may host super-Earths or mini-Neptunes in distant orbits, hinting that Planet 9 might not be an anomaly. Interpretation: Planet 9 represents the next frontier in cosmic exploration. Just as Pluto's discovery in 1930 expanded our understanding of the outer solar system, confirming Planet 9 would mark a new era in planetary science. This search embodies human curiosity and our desire to understand our place in the universe. The discovery of Planet 9 would not only rewrite textbooks, but also inspire future generations to look deeper into the cosmos. As we explore the cosmos, Planet 9's ghostly presence invites us to venture farther and unravel universal mysteries. Whether it's a primordial black hole, dark matter clump, or icy world, Planet 9 reminds us that the cosmos is vast, and our understanding is still in its infancy. This enigmatic quest promises to redefine our place in the universe and inspire future explorers. Part 11. The Rings of Saturn. How long will the iconic rings of Saturn endure? This question haunts astronomers and enthusiasts alike, as the magnificent rings, first observed by Galileo in 1610, face an uncertain future. The rings, which Galileo could not clearly resolve through his primitive telescope, were later confirmed by Christian Huygens in 1655, who described them as a thin, flat ring nowhere touching the planet. This marked the beginning of our fascination with Saturn's most distinctive feature. Saturn's rings are more than just a celestial spectacle. They are a dynamic system in constant flux, composed predominantly of water ice, with traces of dust and rocky material. These rings stretch up to 280,000 kilometers from the planet's surface, yet are astonishingly thin, averaging only about 10 meters in thickness. This delicate structure is under threat from a phenomenon known as ring rain, in which charged particles from the rings are drawn into Saturn's atmosphere along magnetic field lines. This process, accelerated by micrometeoroid bombardment and interactions with Saturn's powerful magnetic field, is gradually eroding the rings at an alarming rate. Scientists estimate that the rings are losing material at a rate of approximately 600 to 1,800 kilograms per second, a staggering amount that underscores their ephemeral nature. Estimates suggest that the rings, which may have formed as recently as 100 million years ago during the Cretaceous period on Earth, could disappear entirely within the next 100 million years. The depletion of Saturn's rings is not just a cosmic curiosity, it is a window into the planet's atmospheric dynamics. As the rings fade, they leave behind a stream of ionized gas that interacts with Saturn's magnetic field, creating a complex interplay of forces that shape the planet's environment. The loss of the rings could have profound consequences for Saturn's climate, potentially altering wind patterns and even the iconic hexagonal storm at the North Pole. This massive storm, larger than Earth, has persisted for decades, its sharp, geometric boundaries defying easy explanation. The storm, first observed by the Voyager spacecraft in the 1980s, has been a subject of intense study. Without the rings, the influx of ionized particles could weaken or distort the jet stream that maintains the storm, causing it to dissipate or transform into something unrecognizable. This could also affect Saturn's auroras, which are produced by the interaction of the solar wind with the planet's magnetic field. The changing dynamics of the rings and their influence on the magnetic field could lead to more vivid or altered auroral displays, painting the planet's poles with new patterns of light. But the rings are not the only mystery. Saturn's moons, Titan and Enceladus, are worlds unto themselves, with conditions that could potentially support life. Titan, the largest of Saturn's moons, is shrouded in a thick, smoggy atmosphere composed primarily of nitrogen, much like Earth's. Its surface is dotted with lakes and rivers of liquid methane, which carve channels and shape features remarkably similar to those found on Earth. However, Titan's frigid temperatures, averaging 179 degrees Celsius, make water ice as hard as rock, creating an alien landscape unlike anything in our solar system. The Huygens probe, which landed on Titan in 2005 as part of the Cassini mission, revealed a world with a dynamic weather system, including methane rain and snow. This cycle of methane on Titan mirrors Earth's hydrological cycle, but with entirely different substances and conditions. Enceladus, on the other hand, is a small, icy moon with a global subsurface ocean hidden beneath its frozen crust. This ocean, heated by tidal forces from Saturn's gravitational pull, may harbour hydrothermal vents similar to those found on Earth's ocean floors. These vents could provide the necessary energy and nutrients to support simple forms of life, making Enceladus one of the most promising candidates in the search for extraterrestrial life within our solar system. The Cassini spacecraft, which explored Saturn and its moons from 2004 to 2017, detected complex organic molecules in the plumes of water vapor ejected from Enceladus's south polar region. These molecules, essential for life as we know it, hint at the possibility of a habitable environment deep within the moon's hidden ocean. Enceladus's plumes, which shoot water vapor and ice particles hundreds of kilometers into space, are so powerful that they contribute to the formation of Saturn's E-ring, the second outermost ring of the planet. This connection between Enceladus and the rings highlights the interconnectedness of Saturn's system. As we unravel the secrets of these distant worlds, we are not just exploring the solar system, we are redefining the boundaries of habitability. Each new discovery challenges our understanding of where life can exist and thrive. Titan's methane lakes, for instance, are not only intriguing for their resemblance to Earth's hydrological cycle, but also for their potential to host exotic forms of life adapted to cryogenic conditions. Similarly, Enceladus's subsurface ocean offers a glimpse into the possibilities of life in environments far removed from the warmth of a star. These moons serve as laboratories for exploring the limits of biology and chemistry, pushing the frontiers of astrobiology into uncharted territories. The study of these moons could also inform our understanding of early Earth, as the conditions on Titan and Enceladus may resemble those on our planet billions of years ago. Observation. The rings of Saturn are not a permanent feature but a transient phenomenon, likely to disappear within the next 100 million years due to the ongoing process of ring rain. Interpretation. The depletion of the rings will have significant implications for Saturn's climate and atmospheric dynamics, potentially altering features like the hexagonal storm and reshaping our understanding of the planet's environment. Speculation. The moons Titan and Enceladus, with their unique conditions, may harbour forms of life adapted to environments vastly different from those on Earth. Future missions to these moons could revolutionize our understanding of habitability and the potential for life beyond our planet. The quest to understand Saturn's rings and its moons is far from over. Upcoming missions, such as NASA's Dragonfly, aim to explore Titan's surface using a drone-like lander, sampling its methane lakes and searching for signs of prebiotic chemistry. Dragonfly, slated to launch in 2027, will be capable of flying to multiple locations on Titan, providing unprecedented access to its diverse landscapes. Meanwhile, proposals for returning to Enceladus with advanced instruments could provide definitive evidence of life in its subsurface ocean. The Enceladus Life Finder (ELF) mission, currently in development, aims to analyze the plumes ejected from the Moon's south pole for biosignatures such as amino acids or other biological molecules. Each step brings us closer to unraveling the mysteries of these enigmatic worlds, revealing not just the fate of Saturn's rings, but the potential for life in the farthest reaches of the cosmos. As we delve deeper into the secrets of Saturn's system, we are not only expanding our knowledge of the universe, but also redefining our place within it. Part 12. The Cosmic Dance. What can the orbits of distant objects tell us about the architecture of the solar system? The outer solar system is a realm of icy bodies and distant orbits, a region where the familiar rules of planetary motion give way to the subtle dance of gravitational interactions. Among these celestial wanderers are the trans-Neptunian objects, TNOs, a diverse group of bodies that orbit beyond the gas giant. Their paths are shaped by the gravitational tug of a hypothetical world known as Planet 9, a rogue planet that remains unseen but undeniable. These TNOs, numbering in the thousands, include well-known objects like Pluto and Eris, as well as countless smaller bodies that drift in the frigid expanse beyond Neptune. Their orbits, often highly elliptical and tilted at steep angles to the ecliptic, defy the orderly alignment of the inner planets, hinting at the presence of an unseen perturber. The Kuiper Belt, a vast region stretching from 30 to 55 AU, is home to over 300,000 TNOs larger than 100 kilometers, each a frozen time capsule from the early solar system. The search for Planet 9 is a journey fraught with challenges. Its distant orbit, estimated to be between 400 and 800 astronomical units from the Sun, places it in the far reaches of the solar system, where the light of the Sun barely reaches. At this distance, the Sun appears as a faint star, providing only about 0.05% of the illumination we receive on Earth. This remoteness makes direct observation difficult, but it also offers a unique opportunity to study the gravitational dynamics of the outer solar system. The faintness of objects in this region requires astronomers to employ the world's most powerful telescopes, such as the Subaru telescope in Hawaii and the upcoming Vera C. Rubin Observatory in Chile, which will scan the sky with unprecedented sensitivity. These instruments are equipped with advanced adaptive optic systems that correct for atmospheric distortions, allowing them to detect objects as faint as 27th magnitude, about as bright as a candle seen from a distance of 2,000 kilometers. By mapping the orbits of TNOs, scientists are piecing together the potential location and characteristics of Planet 9. Its influence extends far beyond its immediate vicinity, shaping the paths of distant objects and leaving a trail of gravitational breadcrumbs that hint at its existence. The orbits of at least 6 known TNOs, including Sedna and 2012 VP-113, nicknamed Biden, exhibit unusual alignments that suggest they are being shepherded by the gravitational pull of a massive distant object. These alignments are not random. They point to a specific region of the sky where Planet 9 might be lurking, invisible but influential. The orbital clustering is so pronounced that the probability of it occurring by chance is estimated to be less than 0.007%, or about 1 in 14,000. Observation. The clustering of TNO orbits is one of the strongest pieces of evidence supporting the existence of Planet 9. Computer simulations have shown that a planet with a mass roughly 10 times that of Earth, orbiting between 400 and 800 AU from the Sun, could explain the observed alignments. However, these simulations also suggest that Planet 9's orbit is highly elliptical and inclined, making it even more difficult to detect. Its closest approach to the Sun, known as perihelion, might be as far as 200 AU, while its farthest point, or aphelion, could extend to 200 AU or more. At such distances, the planet would move at a glacial pace, taking between 10,000 and 20,000 years to complete a single orbit. For comparison, Pluto's orbit, which was once considered the outer boundary of the solar system, has a semi-major axis of just 39.5 AU and an orbital period of 248 years. The hunt for Planet 9 is not merely academic. It has profound implications for our understanding of the solar system's formation and evolution. If confirmed, Planet 9 would be the first truly new planet discovered in our solar system since Neptune in 1846. Its existence would challenge the traditional 9-planet model, including Pluto, that dominated much of the 20th century, and reshape our view of the outer solar system. Moreover, Planet 9's distant orbit could provide insights into the early dynamics of the solar system, including the possibility that it was once part of a larger population of rogue planets ejected from their original orbits during the chaotic early days of planetary formation. Some models suggest that up to 50% of the original planetary embryos in the solar system were ejected into interstellar space, leaving behind only the survivors we see today. Speculation. Some theories propose that Planet 9 is not a native of our solar system, but a captured interstellar object. Its unusual orbit and large size could suggest that it formed around another star and was later gravitationally captured by the Sun. This idea, though controversial, is supported by recent discoveries of rogue planets wandering the galaxy without a parent star. Astronomers have identified at least 70 such objects in nearby star-forming regions, with masses ranging from a few times that of Jupiter to well below the deuterium burning limit that defines brown dwarfs. If true, Planet 9 would offer a rare opportunity to study an extrasolar world up close, shedding light on the diversity of planetary systems beyond our own. Its composition, atmosphere, and internal structure could reveal whether it formed in the cold, dense environments of a molecular cloud, or in the warmer, more chaotic conditions of a protoplanetary disk. The cosmic dance of the outer solar system is a story of invisible forces and hidden worlds. As astronomers continue to map the orbits of TNOs and refine their models of Planet 9, they are slowly revealing the unseen architecture of our celestial neighborhood. Each new discovery, each subtle gravitational tug, brings us one step closer to understanding the grand ballet of planets, moons and comets that share our corner of the cosmos. In this dance, Planet 9 may be the absent partner, unseen but felt, guiding the movements of countless bodies in the vast, silent expanse of the outer solar system. The search for this elusive world is not just a quest to fill a gap in our planetary inventory. It is a journey to uncover the secrets of our solar system's past and its place in the cosmic tapestry. Part 13. The Frontiers of Propulsion. How will we bridge the vast emptiness of space? The distances are almost incomprehensible. Alpha Centauri, our nearest stellar neighbor, is a mere 4.37 light-years away, over 40 trillion kilometers. With current technology, it would take tens of thousands of years to reach it. The dream of interstellar travel is as old as the stars themselves, but the technology to make it a reality remains elusive. Current propulsion systems, from chemical rockets to ion engines, are insufficient for the journey to the nearest star. To bridge the vast emptiness of space, we must think beyond conventional wisdom. The Voyager 1 spacecraft, launched in 1977, is the fastest and most distant human-made object in space, traveling at a velocity of about 17 kilometers per second. At this speed, it would take over 70,000 years to reach Alpha Centauri. The limitations of chemical propulsion are starkly evident. Even advanced ion drives, like those used on NASA's Dawn mission, which achieved speeds of up to 41 kilometers per second, would still require millennia to traverse interstellar distances. The challenge is not merely about speed, but about sustaining that speed over unfathomable distances and timescales. Nuclear pulse propulsion, first proposed during the Cold War, is one such possibility. Conceived in the 1950s as part of the Orion project, this method envisioned a spacecraft propelled by a series of nuclear explosions detonated behind it. Theoretically, it could achieve velocities of up to 3% the speed of light, reducing the travel time to Alpha Centauri to roughly 130 years. But the challenges are immense, from the technical hurdles of synchronizing millions of detonations to the ethical concerns of using nuclear explosions in space. The potential for radioactive fallout and the violation of nuclear test ban treaties make this approach controversial, despite its scientific feasibility. The idea of nuclear propulsion has evolved in recent decades. The nuclear thermal rocket, NTR, which uses a nuclear reactor to heat propellant, offers a less dramatic but more practical alternative. NASA's Kilopower project, for instance, aims to develop small, reliable nuclear reactors for space missions. These reactors could power electric propulsion systems such as Hall-effect thrusters, enabling sustained acceleration over long durations. While not as fast as nuclear pulse propulsion, NTRs could still reduce travel times to the outer solar system by years, making missions to destinations like Neptune or even the Kuiper Belt more feasible. Another innovative concept is the light sail, a thin, reflective sheet propelled by powerful ground-based lasers. This approach, championed by the Breakthrough Starshot initiative, could achieve speeds of up to 20% the speed of light, making interstellar travel a reality within our lifetime. The project envisions a fleet of tiny spacecraft, each weighing just a few grams, accelerated to relativistic speeds by a phased array of lasers. However, the technical challenges are daunting. The synchronization of millions of lasers, the development of materials capable of withstanding the intense radiation, and the precision required to aim the lasers at such small targets over vast distances are all hurdles that must be overcome. The Breakthrough Starshot initiative, launched in 2016, aims to send these nanocraft to Alpha Centauri within a generation. Each craft would carry miniaturized sensors, cameras, and communication devices, allowing us to capture the first close-up images of another star system. The data returned from such a mission would revolutionize our understanding of exoplanets, stellar evolution, and the potential for life beyond our solar system. However, even if the technical challenges are surmounted, the cost and energy requirements of such a mission are staggering. The laser array alone would need to be kilometers in diameter and powered by gigawatts of energy, dwarfing any existing terrestrial infrastructure. Beyond nuclear propulsion and light sails, other concepts pushed the boundaries of physics and engineering. Antimatter propulsion, for example, could theoretically achieve speeds approaching the speed of light. Antimatter annihilates with ordinary matter, releasing an enormous amount of energy. A spacecraft equipped with an antimatter engine could harness this energy to propel itself to relativistic velocities. However, antimatter is exceedingly rare and difficult to produce, requiring immense amounts of energy and advanced technology. Current estimates suggest that producing even a gram of antimatter would cost trillions of dollars and require decades of research. Fusion propulsion, another promising avenue, seeks to harness the energy released by nuclear fusion reactions, the same process that powers the sun. Unlike fission, which splits atomic nuclei, fusion combines them, releasing vast amounts of energy with minimal radioactive waste. A fusion-powered spacecraft could achieve speeds of up to 10% the speed of light, making interstellar travel more feasible. However, sustained and controlled fusion reactions have proven elusive, despite decades of research. Projects like ITER, the International Fusion Experiment, aim to demonstrate the feasibility of fusion power, but scaling this technology for space propulsion remains a distant goal. As we explore these cutting-edge concepts, we are not just searching for a means of propulsion, we are searching for the limits of human ingenuity. The frontiers of propulsion are a testament to our relentless pursuit of the unknown, a journey that could one day take us to the stars. Each breakthrough brings us closer to overcoming the tyranny of distance, to bridging the vast emptiness of space. Yet, with every step forward, new challenges emerge, reminding us that the path to the stars is not a straight line, but a winding odyssey of discovery and innovation. Observation. The quest for interstellar propulsion is not merely about reaching the stars, but about pushing the boundaries of science, engineering, and human ambition. It is a journey that tests our ability to cooperate, innovate, and dream on a cosmic scale. Interpretation. The technologies we develop in pursuit of interstellar travel will have far-reaching implications beyond space exploration. Advances in nuclear fusion, laser technology, and materials science could revolutionize energy production, transportation, and manufacturing on Earth, creating a more sustainable and prosperous future for humanity. Speculation. Will we ever reach the stars? The answer depends not only on our technological prowess, but also on our collective will to explore, to question, and to dream. If history is any guide, the human spirit is capable of extraordinary feats. The frontiers of propulsion are not just a scientific challenge, but a test of our shared humanity, a test we are destined to pass. Part 14. The Echoes of Life. Can we detect the whispers of extraterrestrial civilizations? The search for extraterrestrial life is not just about finding planets. It's about understanding the conditions that make life possible. Biosignatures like oxygen, ozone, and methane are the starting point, but they are not the whole story. To truly grasp the potential for life beyond Earth, we must look for technosignatures, evidence of advanced civilizations that have harnessed technology to alter their environments. These civilizations might have engineered their atmospheres, constructed vast megastructures, or even manipulated the light emitted by their stars. The concept of a Dyson sphere, for example, proposes a hypothetical structure that could encompass an entire star to capture its energy, a feat that would drastically alter the star's observable characteristics. Projects like Breakthrough Listen are scouring the cosmos for these technosignatures using vast networks of radio telescopes to detect signals that could indicate the presence of intelligent life. The Breakthrough Listen initiative, launched in 2015, has already surveyed millions of stars and hundreds of galaxies, collecting petabytes of data in its quest to identify artificial signals. But the search is fraught with challenges. The cosmos is a noisy place, filled with natural phenomena that can mimic the signals we seek. Pulsars, for instance, were initially mistaken for artificial signals due to their precise, regular pulses, earning them the early nickname "Little Green Men." Distinguishing a true technosignature from background noise is a monumental task, but it is one that scientists are tackling head-on. To filter out the cosmic cacophony, researchers employ advanced algorithms and machine learning techniques. These tools help identify patterns that might otherwise go unnoticed, such as the repetitive sequences or mathematical structures that could signify an intentional broadcast. For example, the WOW signal, detected in 1977, remains one of the most intriguing unexplained events in radio astronomy. This narrow-band radio signal, which lasted for 72 seconds, has never been repeated or explained, despite decades of follow-up observations. Its frequency and intensity were so unusual that it sparked speculation about an extraterrestrial origin, though no definitive proof has emerged. As we sift through the data, we are not just searching for signals, we are searching for meaning. Each potential signal is a piece of the cosmic puzzle, a clue that brings us one step closer to understanding our place in the universe. The detection of a technosignature, if it ever occurs, would revolutionize our understanding of the cosmos and our role within it. It would challenge our philosophical, scientific, and cultural frameworks, raising questions about the nature of intelligence, the diversity of life, and the potential for interstellar communication. Observation. The search for technosignatures requires not only technological sophistication, but also a deep understanding of the potential forms that extraterrestrial intelligence might take. Civilizations far older than ours could have evolved in ways that are unimaginable to us, using technologies or communication methods that we have yet to conceive. For instance, a civilization that has mastered quantum communication might transmit information in ways that are undetectable to our current instruments. Interpretation. The absence of evidence is not evidence of absence. The fact that we have not yet detected technosignatures does not mean that extraterrestrial civilizations do not exist. Instead, it could indicate that our methods are still too limited, our searches too narrow, or our assumptions too Earth-centric. The cosmos is vast, and the window of time during which a civilization might be detectable, what astronomers call the observability window, could be extraordinarily brief. A civilization might rise and fall in a cosmic blink, leaving no trace of its existence. Speculation. What if the first techno-signature we detect is not a radio signal but something far more subtle? Perhaps it will be a pattern in the light of a distant star, altered by an advanced civilization to convey a message. Or it could be a strange object drifting through interstellar space like Oumuamua, the first known interstellar object to pass through our solar system. Its elongated shape and unexpected acceleration have fueled speculation about its origins, though most scientists lean toward natural explanations. Whatever form the signal takes, its discovery would mark a turning point in human history, a moment when we realize we are not alone in the cosmos. The search for the echoes of life is, at its core, a search for connection. It is a quest to bridge the vast distances of space and time, to find common ground with beings who may share our curiosity and our desire to understand the universe. Whether we find those echoes tomorrow or 1,000 years from now, the journey itself is a testament to our collective spirit of exploration. And in the silence of the cosmos we listen, hoping to hear the faint whispers of other worlds. Part 15. The Final Countdown. Are we on the brink of a cosmic revolution? The journey to the stars is not just a dream, it is a testament to human ingenuity, our relentless quest to bridge the vast emptiness of space and find our place among the cosmos. From the discovery of exoplanets like Proxima Centauri b, a potentially habitable world orbiting our nearest stellar neighbor, to the ongoing search for technosignatures, artificial signals that could indicate the presence of advanced civilizations, we are on the brink of a cosmic revolution. This is a moment when science and imagination converge to redefine the boundaries of what is possible. The cosmos, once a domain of myth and speculation, is now within our reach, and the possibilities are as limitless as the stars themselves. Imagine standing on the surface of Mars, looking up at a night sky filled with unfamiliar constellations. This is no longer a distant fantasy, but a tangible goal within our grasp. NASA's Mars 2020 Perseverance rover is already collecting samples that future missions will return to Earth, potentially containing evidence of past microbial life. Meanwhile, SpaceX's Starship program aims to establish a human presence on Mars within the next decade, transforming our relationship with the red planet from one of distant observation to direct interaction. Every step we take on Mars brings us closer to understanding whether life ever emerged there, and by extension, whether it could exist elsewhere in the universe. As we stand on the precipice of this new frontier, we are not just exploring distant worlds, we are exploring the limits of our knowledge, the potential of our technology, and the depths of our curiosity. The stakes are high, the challenge is immense, but the potential payoff, unfathomable. Consider the scale. The Milky Way galaxy alone contains an estimated 100 billion stars, and recent studies suggest there could be as many as 300 million potentially habitable planets within it. Each of these worlds is a potential cradle of life, a beacon of hope in the cosmic expanse. The questions we ask about life, about our place in the universe, are not abstract. They are urgent, pressing, and deeply human. The search for extraterrestrial life is now a multidisciplinary endeavor, drawing on fields as diverse as geology, biology, chemistry, and astronomy. For instance, the field of astrobiology seeks to understand the conditions and processes that could give rise to life beyond Earth. Researchers study extremophiles, organisms that thrive in extreme environments on our planet. to infer the possibilities for life in the harsh conditions of other worlds. The discovery of microbes living in deep-sea hydrothermal vents or in the acidic pools of Yellowstone has expanded our concept of habitability, making worlds like Jupiter's moon Europa or Saturn's moon Enceladus prime targets in the search for life. The question that echoes through the cosmos, are we alone, is not just a query of scientific inquiry. It is a reflection of our deepest desires to explore, understand, and connect with the vast, wondrous universe that is our home. As we gaze into the heavens, armed with the power of modern science and the relentless spirit of exploration, we stand on the edge of possibility, ready to take the next giant leap into the unknown. The search for extraterrestrial life is no longer confined to the realm of science fiction. It is a tangible, ongoing pursuit driven by breakthroughs in astrobiology, exoplanet detection, and the burgeoning field of astrochemistry. Every new discovery, from the detection of organic molecules in distant star systems to the identification of potentially habitable environments on moons like Enceladus and Europa, brings us one step closer to answering the ultimate question. Consider the recent detection of phosphine gas in the clouds of Venus. While the findings remain controversial, the presence of this gas, which on Earth is associated with biological processes, has reignited scientific interest in our closest planetary neighbour. Missions like NASA's Da Vinci Plus and ESA's Envision are being planned to further investigate Venus's atmosphere and surface, seeking clues to its geological and possibly biological history. Even worlds once thought to be inhospitable are now being re-evaluated, demonstrating how our understanding of habitability continues to evolve. The march of progress is unstoppable. In the last decade alone, the Kepler Space Telescope and its successors have identified over 5,000 exoplanets, a number that grows almost daily. Among these discoveries are worlds like TRAPPIST-1F, a potentially Earth-like planet orbiting a red dwarf star just 40 light-years away. These findings are not just numerical entries in a scientific catalogue. They are invitations to imagine, to dream, and to explore. Each exoplanet is a reminder that our solar system is not unique, that life could be thriving elsewhere, waiting to be discovered. The cosmic revolution is not just about finding other worlds. It is about finding ourselves in the process. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018, has already discovered over 2,000 exoplanet candidates, including several in the habitable zones of their stars. TESS builds on Kepler's legacy by focusing on nearby stars, making the exoplanets it discovers prime targets for follow-up observations with ground-based and future space-based telescopes. This synergy between missions allows scientists to characterize exoplanet atmospheres searching for biosignatures, chemical indicators of life, such as oxygen, methane, or water vapor. The first detection of such a signature would mark a turning point in human history, providing the strongest evidence yet that we are not alone. Yet the challenges are daunting. The distances involved are almost incomprehensible. Proxima Centauri b, one of our closest potentially habitable neighbours, is 4.2 light-years away. With current technology, a journey to this world would take tens of thousands of years. But projects like Breakthrough Starshot, which aims to develop ultra-fast, light-driven nanocraft capable of reaching Alpha Centauri within a human lifetime, offer a glimmer of hope. These initiatives are not just technological feats. They are testaments to the human spirit, proof that our ambition knows no bounds. The cosmic revolution will not be easy, but it will be worth it. Breakthrough Starshot envisions sending a fleet of tiny spacecraft, each weighing just a few grams, to the Alpha Centauri system at speeds up to 20% the speed of light. Propelled by ground-based lasers, these nanocraft could reach their destination in just 20 years, sending back data and images of the system's planets. While the engineering hurdles are significant, the project represents a bold step toward interstellar exploration, demonstrating that even the vast distances between stars are not insurmountable barriers to human ingenuity. And what of the consequences if we succeed? The discovery of life beyond Earth, even in its most microbial form, would shatter the walls of our solitude. It would rewrite our understanding of biology, chemistry, and evolution. It would force us to reevaluate our place in the universe, to confront our own insignificance and our profound connection to the cosmic whole. But the search does not end with microbes. The quest for intelligent life, for civilizations that may have arisen elsewhere in the galaxy, is perhaps the most audacious of all. Projects like the Search for Extraterrestrial Intelligence, SETI, have been scanning the skies for decades, listening for signals that might indicate the presence of other technological beings. So far, the universe has remained silent, but the silence is not defeat. It is an invitation to keep searching, to keep listening, to keep believing. The SETI Institute's Allen Telescope Array, located in Northern California, is one of the primary tools in the search for extraterrestrial intelligence. Capable of observing thousands of star systems simultaneously, the array listens for narrowband signals, artificial radio emissions that could indicate the presence of advanced civilizations. While no definitive signals have been detected yet, the search continues to expand, with new telescopes and observatories joining the effort. The upcoming Square Kilometre Array, SKA, with its unprecedented sensitivity, will be capable of detecting signals from distant galaxies, vastly expanding the scope of the search. The silence also raises questions. The Fermi paradox, named after physicist Enrico Fermi, asks a simple but haunting question. If intelligent life is common in the universe, where is everybody? The absence of clear evidence for extraterrestrial civilizations has led to countless theories, from the Great Filter hypothesis, which suggests that intelligent life may be rare due to some catastrophic event or barrier, to the zoo hypothesis, which posits that advanced civilizations might be deliberately avoiding contact with us. These ideas are not just academic exercises, they are reflections of our own fears and hopes, projections of our own existential uncertainties onto the cosmic canvas. One of the most intriguing explanations for the Fermi paradox is the rare Earth hypothesis, which argues that the emergence of intelligent life requires an extraordinarily rare convergence of circumstances. According to this theory, factors such as a stable star, a habitable planet with a large moon to stabilize its axial tilt, and the presence of plate tectonics to regulate climate may be so uncommon that Earth is one of the few, or perhaps the only worlds where such conditions exist. If true, this would make humanity a cosmic anomaly, underscoring the importance of our search for life elsewhere. But the search continues, undaunted. The next generation of telescopes, like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, will peer deeper into the cosmos than ever before, revealing worlds and phenomena we can barely imagine. Ground-based observatories like the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, will push the boundaries of our knowledge, allowing us to study distant stars and galaxies with unprecedented clarity. These instruments are not just tools of science. They are extensions of our senses, our eyes and ears in the cosmic void. With them, we will not just observe the universe, we will become part of it. The James Webb Space Telescope, launched in 2021, is already revolutionizing our understanding of the universe. With its infrared capabilities, it can peer through dust clouds to observe the earliest stars and galaxies, shedding light on the universe's infancy. It will also study the atmospheres of exoplanets, searching for biosignatures and providing insights into their potential habitability. Meanwhile, the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct wide-field surveys of the sky, identifying thousands of new exoplanets and mapping the structure of the universe with unparalleled precision. In the quiet of a starlit sky, the question lingers: are we alone? The search for life beyond Earth is not just a scientific endeavor. It is a profound exploration of our place in the cosmos. As we stand on the brink of discovery, armed with the power of modern science and the relentless spirit of exploration, we are not just searching for answers, we are searching for meaning. The cosmos is vast, its mysteries infinite, but our quest for understanding is unyielding. From the discovery of exoplanets like Proxima Centauri b to the search for technosignatures, we are on the verge of a cosmic revolution, a moment when science and imagination converge to redefine the boundaries of what is possible. As we gaze into the heavens, we are not just exploring distant worlds. We are exploring the limits of our knowledge, the potential of our technology, and the depths of our curiosity. The journey to the stars is not just a dream, it is a testament to human ingenuity, our relentless quest to bridge the vast emptiness of space and find our place among the cosmos. And as we stand on the precipice of this new frontier, we are reminded that the question that echoes through the cosmos, "Are we alone?" is not just a query of scientific inquiry. It is a reflection of our deepest desires to explore, understand, and connect with the vast, wondrous universe that is our home. The call of the cosmos is clear, and we are ready to answer it. The future of human exploration hangs in the balance, and the possibilities are endless. As we take the next giant leap into the unknown, we stand on the edge of possibility, ready to embrace the mysteries of the universe and redefine our place among the stars. The cosmic revolution is not just a distant goal, it is a journey we are already undertaking. With each new discovery, each technological breakthrough, and each bold mission, we inch closer to understanding our place in the universe. Whether we find microbes on Mars, biosignatures in the atmospheres of distant exoplanets, or signals from advanced civilizations, the search for life beyond Earth will fundamentally transform our relationship with the cosmos. And in that search, we will not only discover the universe, we will discover ourselves. End of transmission.